As you can see up here, how it looks like a, you know, these synapses talk to each other by throwing photons at each other, right? There's gaps. It's just doesn't this look just like a photon clock though, moving, right? Everything's the same way with these atoms in this hand. Just think of two atoms as a photon clock. And when you move, you're making the information carrier, the photon, travel longer, and it has a set speed. So if you make it travel longer, that means information takes longer. Physics takes longer, right? And this all works out perfect and fine until I realized here, and this is why the longitudinal, this thing right here, well, what happens, it works perfectly with this, but what about when you're doing this and you're going to the right? You know what I mean? Yeah, it ain't going to work out too well. So this is what we have. When I say now, you need to throw, the first atom needs to throw the photon, right, the information carrier, and then wait, right, for reply, and then move, or do whatever the photon, you know, the information carriers tell her meant to do. So look, this is the first second, the hand, right? Now he throws a photon, just like last time, to the second guy, but he can't throw it vertically because the next second the hand's going to be over here, right? So he throws it diagonally, right? But he does not move, okay? Now this guy, okay, this is the same as this guy, right? They're both atoms, right? This is the guy that caught the photon this one through, right? Now what he does is he throws out two photons, right? One in each direction, one to tell the other atom, you know, the third atom, hey, I want you to accelerate, right? And the other atom, why does he throw it back to the second atom? Because you'll see. And then after this second atom gets that photon, then it moves, okay? And I'm going to get into why in a second here when we get into the longitudinal, you know, this kind of thing right here, right? And then that just happens over and over. Now this first atom already moved. This one threw a photon this way and this way. So now it's this guy's, you know, he's got the whatever. So the next second, he throws photons both ways, and one of them is going back to this first one that threw a photon to him, right? Then when the second atom gets this back, then he moves. The reason why, and I want you to notice too, either way on this type of clock right here, right, we can use a half Planck second or we can use a full Planck second, meaning we can use this one thing here as a Planck second, or we can say back and forth is a Planck second, okay? Doesn't really make a difference because you can see it's half. It's exactly half. So if you move, okay, but let's check out the longitudinal clock, right? Now this clock hand was moving over to the right, right? This clock hand is moving up, right? These first four dots, right, going up and down, that's the clock hand, right? And it wants to turn, right? It wants to turn this way. Same way it wants to turn, right? The clock it hasn't moved. The clock is still, this hand is still like this, right? It's just that instead of the frame moving to the right, now the frame is moving up. So now, when this first atom throws out a photon, you know, this second atom is going to be moving, it's going to be way up here, right? It's going to be like a little bit more, you know, it's going to move from here to here, right? So look at the photon when he throws it. He throws it long, it's going to be long instead of short. If he threw one back, it would be that short, right? See how it's a little, I drew a little red one there? But let's say it was one-way communication, okay? What would happen is the second one would get this would throw the photon, and then it, you know, it would move. This one would get a photon, throw it, move, and so just like over here, right? And they would all have the same Planck second. You see how that long blue Planck second. But I want you to think about, what if the frame was going this way? Now it would be this, see this little red thingy, you know, how you got a big one and a long one when you do it longitudinal? Yeah. Now the Planck second would be this little tiny thing. See, that's why it can't be a one two-way communication. Because if your clock is this way, it's going to tick different than your clock going this way, and both of those are going to tick different than if you have this kind of clock and you're going, you know what I mean? They'll all be ticking the wrong ways because they're Planck lengths or their Planck second, which is the same thing, are all different. So physics are going to run at a different rate in their frame. That can't be. They all have to have this. They all have to run the same way. You know what I mean? They all have to have the same Planck second. That's for damn sure, right? You can't, because your clocks would run differently, right? Depending on how you set them. If you set them like this or whatever, you know what I mean? Okay, but look over here. See, if you have your clock like we regularly do it, right? You split it up into halves. You know, you're bouncing to one plate to the other. But look at the longitudinal one, right? The blue line is so long. The red line is only a tiny bit over there, right? Look at that little tiny bit of red, right? But if you go both ways and say that that's a Planck second, now look, they're the same second, right? So no matter, you know, even if you have a longitudinal clock going this way or you have it going this way, you know, relative to your frame, it won't matter. That little tiny, you know, if you have one-way communication, you'd have that little tiny thing going one way. You'd have this big tick going the other way. Your things would work differently. But this way, either way you go, right? This one uses the big blue line and gets communication back from the red. That's, you know what I mean? It takes this Planck, you know what I mean? Same way this. So if they both take the blue and the red, they end up with the same thing, which is the same thing as you have with the clock like this, right? Same thing, same length. See these? They're same length. And a Planck second, okay? Nobody can see a Planck second. So this discrepancy where things are going weird or whatever don't matter. Because no physics. See, that's the whole thing. No physics can happen, right, in between a Planck length, right? So if your Planck length goes up, you know, you have a long distance going one way and then it bounces back and you only got a little distance, it doesn't matter. Because during that time, zero physics are taking place, right? During a Planck second, nothing is happening except for transfer of information from information carriers, right? So no physics is taking place. So it doesn't matter if, you know, you have Willy Wonky long way going this way and short going the other way. It doesn't matter. Nothing's happening during that time. You're just transferring information. Who cares? So if you're longitudinal, right, you would throw your long blue photon, because this second atom is moving up, right? It would catch it, but you would not move yet, right? You would wait until it threw a photon back at you, right? And you can see how little of space it is, and then you move, okay? Just like over here, right? It's a two-way. That way, if you have a clock facing the other way, it does the same thing in the opposite fashion. It'll throw a little photon out, you know, and then when it bounces back, it'll be long. But the little line and the long line will add up the same way as this long line and the little line lands up. And these will add up the same way as the clock like this, right? They'll all have the same Planck second in their frame, right? Even if they're longitudinal like that. See that? We solved this longitudinal thing, how it happens, right? See, and the reason why we do this, right, this way is all the physics, all the atoms are obeying the same Planck second. You have to have the same, everyone has to have the same Planck second, or physics would work differently with different atoms, you know what I mean? It won't work out right. To keep the Planck second the same, okay, because let's say you have you got these two synapses are this direction, right? You throw it down here, it comes back. You know, that tells you what a Planck second is. That way, your clocks that are going this way, right, that aren't longitudinal, this way, the Planck second is the same. It's the same. It's the exact same thing. You know what I mean? That way you get the same time dilation, you get the same, everything, all your physics is the same. You know what I mean? And when you register this as a Planck second, the full thing, you know what I mean? Then you're basically you're talking about two-way speed of light. You know what I mean? And it doesn't matter what it goes one way or the other. It just matters that it goes c, you know, relative to space-time. That's all that matters, really. Because they can't understand that c is always relative to, you know, space-time, not to people. They keep putting it, oh, c is relative to him, and him. No, the universe. They love. Stop putting Einstein's postulates over the universe's postulates, okay? The universe trumps Einstein. I hate to tell everyone this, but you can't change that fact. That space-time, that's what makes time. It wouldn't work. Nothing would work if that's one fact I know. Is light and information carriers, they travel at the speed of c relative to space-time. Not people moving, not people stationary. They don't care about your freaking frame or your postulates, okay? That's going to happen no matter what. You can't stop that or change it. Yeah, the red man's light gets to the black man first, but the time it takes to process the information, even if he was a detector instead of a person, the time would offset, and it would be the same as the blue man. You know, he's going to get to see the blue man's light come later, but it takes time to process because you need back and forth communication between all your synapses, right? Because they could be oriented any which way, right? So the only way to offset that is to go by two-way communication. If you do that, your Planck length, now you can, it doesn't matter. It's just this guy gets hit first by the light, and it takes him, his processes, his brain, you know, working in these different configurations, it takes him time to process that, takes longer. This way, the other direction, takes, you know, it gets the information quick from the blue guy, but it takes, you know, you can see that you can see the information, getting it and processing it is the same length. It's the same Planck length. It's the same thing. And this is what makes everything, you know, so that no matter what configuration you're in, your clock, your synapses, your atoms in a clock, your atoms in anything, the only way it can all work out is if you get if you have to have two-way communication. This is why we can never do the speed of light. You know, we have to do it always two ways. Because there's no such thing as one-way information. It doesn't exist. It's just a fantasy. Okay, there's no such thing. You need two-way communication to have any kind of physics or any kind of thought or any kind of electronics or any kind of acceleration or anything. You need two-way communication. This is a fact. This explains why the Planck length needs to, it's not just up and down, it's up, down, you know, it's two. You got to have an up and a down. You know, I thought the Planck length was just going up. No, it's going up and down. So that the longitudinal clock and all the clocks will have the same Planck length, same Planck second, which is going up and down, because they're always equal that way. If you can't see into the Planck second, then you'll never see, this black man will never see that one way the speed of light is 1.5 and the other way it's 0.5. He'll never know, because his processing in that direction is slowed down or sped up by the proportional, you know, ality, so it can all come out that it's 1c in all directions. Okay. This is how all physics can work the same in the same inertial frame, moving at the same constant velocity. How do things? This is how they all sync up.